I'm very pleased to have Tobias with us. He's a technical lead for the record plus technology at AdaCore, and he will explain what this technology is, which is also includes like streaming protocol and so on.
Hello everyone. I want to start with a question. Do you think that images can be malicious? Do you fear that someone could send you a malicious image on your smartphone?
Yes.
I think you should. So just end of last year, an exploit chain was found in iPhones with an up-to-date iOS at this time. And an attacker was able to specially craft an attachment of an iMessage, and by just sending this image to a victim, he could compromise the iPhone and get full control over it. So especially interesting thing is that there was no interaction needed from the victim. So just by receiving the image, the iPhone got compromised. And that's not an exception. We have seen similar issues before, and we will probably see similar issues also in the future. It's also not that just iPhones or smartphones in general are affected. All software that communicates somehow can be affected by these problems. So why is passing data still a security risk? To answer this question, let's have a look at a simple example. So here we see a UDP message. UDP message is quite simple. We have 4 header fields with a fixed size of 2 bytes per field. The first 2 fields are the source port and destination port. We have a length field and a checksum field. And after that, we have actual data that you want to transmit. When we want to pass this message, it's important to know what the length field actually represents. And in this case, it's not the length of the data, it's actually the length of the whole message. So we have also to take the length of header in account. So the typical representation when you see would be just using C-struct. So just setting all fields by fields of a struct. For example, we can use for all the header fields just integers or integers with 16-bit length. And for the data fields, we can use an array of bytes. The nice thing of this simple representation is we can just map it on a buffer and then just access the fields of the struct to get actual value. When we have, for example, a length field which has the value 11, we have to make sure that we also subtract the length of the header to get the actual length of the data. So to access the actual data, we need to know, or we have to calculate the length. In other cases, everything is fine, it's okay, it works. But there are different coding cases which have to be checked by the developer, which are not encoded in the struct. So for example, if we have a length which is much bigger than the actual length of the message, and we just don't check that, we get a buffer overflow. And a buffer overflow is the typical beginning of an exploit chain. There are some other cases when we don't check that the length is in a range which is expected. For example, we set a length of 0 and then just immediately subtract the length of the header, of it, we get an integer overflow, integer underflow in this case. And the effect will be essentially the same. We get a buffer overflow. And this is the beginning for an attack. And that's just not a theoretical example. We have seen similar issues in the past. You probably heard of the well-known heartbeat vulnerability, where the root cause was also a missing language check. But there are many other issues. We have seen multiple vulnerabilities in Bluetooth, like Quacktooth, Blueborn. There were issues in DNS, and various issues in TCP/IP stacks. And all these examples that you see here are just a small selection. It's just the ones which have fancy names and have a fancy logo on them, but there are many more. And also every day we see new such issues. So the issue is not solved. We still have this issue. We need a better solution for that. And that was the motivation why we started working on Reiher. Reiher is a toolset to create correct and secure protocol implementations. At the center of our toolset is the formal protocol specification. It's a textual representation of the protocol in a custom domain-specific language. It's explicitly tailored for this purpose. And it has essentially two parts. So on the one side, you have the form message specification, which describes how the data structures are formed. And on the other side, we have the formalization specification, which describes how the messages flow through the system, how the data flow looks like. And then around this formal protocol specification, you have different tools. You have as one tool the verifier, which actually checks that the formal protocol specification is correct, that there are no errors in the specification, which could lead to problems when we later on want to generate this code to an actual implementation. So that's the requisite for the code generator, that the protocol is verified, and then you can generate code which is verifiable out of the box. We have a test code generator, which allows on one side to validate the code generator, so that the code generator actually does the right thing. But you can also use the test code generator, the test case generator, to validate the existing application and see if the formal specification is conform to the application or if the application has any implementations error in it. We have a simulator tool which allows to load the formal specification in a Python program so that you can easily use the formal protocol specification in small tools and also validate the application with that. Then there's a validator which allows to validate the specification against samples of an application. So you can track of an application how the message look like and then check against the protocol specification if these methods are correctly identified as valid or invalid according to the specification. We have a modular component which provides some IT support to make it easier for a domain expert to actually describe the protocol from an formal specification. And there's also a converter component which allows to take formal specifications and transform them in our Retterflux specification. Let's look at the typical workflow. So at the first stage, we have a conversion step. So if there's already some formal specification, we can use that to transform it in our Retterflux specification. So far, what we have is a converter which allows to transform Aliana protocol registries. These registries are typically a list of nil constant pairs, and transforming these in constant pairs manually would be very tedious and error-prone, and this can be automated. What we are currently also working on is on a converter which allows to transform DNS presentation language into Retterflux specifications. So this DNS presentation language was first introduced in JS 1.3 and later on also used in DJS 1.3, and maybe we also saw that it's also used in message.js security. Then we come to our actual specifications. So our specifications are modular, so you can represent one aspect of a network stack. So typically, you can see one specification as one representation of a network layer. And then you can combine these building blocks to get the actual specification you want. So you can see the specification as a building block and then form the overall specification with the features you need for a specific use case. Iteratively, you would also check that the specification is correct, do model verification, and ensure that there are no errors in it. If you have a verified specification, you can then also use the validation, check that the specification is conform to an existing application. That's a typical issue also which we have seen with existing standards. So implementations claim to represent a specific standard, but in reality, there's certain details which are different, and such differences can be found in the validation standard. You can also validate it by using a Python program, but you can also use this Python program where you load the specification and then to generate messages or pass messages to create small tools which accompany the actual implementation. Then you have the code generation step where we generate our code. And this generation step can be also configured so that you have really the possibility to make your program as small as possible by defining buffer sizes and memory allocations. And all the code which we generate is file code and can be automatically improved so that we can be sure that's right. What this means exactly, I will tell you in the later slide. Well, let's go back to our initial example. So we've seen just using a string to represent the message format is not a good way. We need a representation which not just has the fields and with their size, but also includes all the areas which we need and also the relation between the fields. And for this purpose, we use regular functions in bidirectional acyclic graph. In this graph, each field of a network is represented by a node, and the links between the nodes define the order of the fields. Each node has also a type which defines on one side how long it is. So in this example for the header fields, we define an integer type which is a bit long integer. But we can also have other cases like the data field, which we have here as an opaque field, and opaque just represents an arbitrary byte array. But what we need here is that we also define a relation between the data field and length field, and we do this by adding a size aspect to the data field. In the size aspect, we define the data length depends on the length of the data field defines the length field and how we calculate it. When you wonder why we modify it with H here, all the sizes and regular flux are represented as bits. The nice thing of having such a formal representation is that we can check that this model is correct. And if we would check this model which you have seen here, we would get an error because it's still not correct. Maybe the data would have a negative size, and that's not correct. We have to check these problems, and there are an option to do it. So one option would be adding explicit invariants. So on each link of this message, we can add conditions. For example, here we can add a condition that the length field must be have to evaluate. And if that's not the case, then the method would be considered invalid and would be rejected. We could also encode this restriction in the type of the length field and create a new specific type for length. And also encode in this range integer that we have at least an integer which has to evaluate. The effect is the same at the end if this constraint would be fulfilled during parsing, then it's actually rejected. Here you see that even for this very simple method UDP, there is potential to do mistakes during the implementation. But in reality, not all messages are that simple as UDP. They're much more complicated messages. You can have messages where the format depends on values of previous fields. You can have optional fields. The size of fields can depend on values of previous fields and similar things. You can get really complex models, and there the power of this direct acyclic graph representation really shines. What do we get from the message verification? So in message verification, we get, for example, that fields cannot overlap, that there are no holes in a message, that in our direct acyclic graph there are no fields which are unreachable or there are no cycles in it. We also check that all conditions have contradictions so that there is no valid message at all. And also if there are conditions which define the message format, we also check that these conditions do not overlap. Because overlapping would mean here that it's not deterministic which path we would need to take, and then the parsing will be not deterministic. So doing proofs on model level is also very helpful and so on. But just trying to put something in this formal specification, you will find errors which we probably wouldn't have found by just looking at the informal specification. But what we actually want to have at the end is an implementation which is correct. And by implementing something from a specification, we can introduce more errors. It's easy to forget some checks, and these errors we also want to prevent. And that's why we use a language which is able to be verified, where you can do program verification. The language which we use is called Spark. It's a language which is based on the language Ada, and it extends Ada by additional aspects to enable the static analysis of the code. So what Spark, for example, adds is preconditions and postconditions to functions and invariants to types and similar things. And by these additional aspects, we can define how the code actually should behave. Ada is also a compiled language, has minimal runtime requirements, and so it's also a good fit for applications where you need minimal resource requirements. So what do we get by program verification? You get, for example, that memory safety is fulfilled, so that there are no errors like buffer overflows. But we can even go a step further and prove absence of runtime errors at all. So also things like integer overflows that they are not intended are detected by the tools. Even one step further, we can also prove function correctness. By adding contracts, we can ensure that the program behaves as we intended it to do. For example, when we create a parser for a message, we can ensure that the fields of the message can be only accessed after the message has been validated. For reflux, all these contracts which need to be generated are generated automatically. So the goal is really to have an automatic solution so that no manual changes on generated code is needed. So far, we've only looked at data structures, but an important part of protocols is also the data flow, how do the messages flow through the system. And for this purpose, we have added split state machines to describe the behavior of an endpoint. In the split state machines, we have a global and a state local context. In each state, we can execute actions. These actions could, for example, be reading messages from the channel, from the outside world, or sending messages, or also doing calculations. We can also call external defined functions. For example, when we want to use existing crypto primitives, we don't need to implement them, re-implement them in Firefox itself, but we can use them in our specification. Between the states, we have transitions, and depending on the session global or the state local state, we can decide which state we follow. So the main goal for the session applications at the moment that we can proof of build Spark code at the end. So what we want to achieve is absence of runtime errors. We also plan to improve this further so that the higher proofs possible, but that's currently not the case. Let's have a look at an example. So we have seen how Firefox works, but how did you use Firefox to harden NVIDIA's computational computing? So some time ago, NVIDIA saw a growing need for safety and security, and formal methods was an option which they identified as a solution. So what NVIDIA did was using now, what NVIDIA does now is using Spark to implement its critical firmware instead of using C as it did before. And one of its use cases is confidential computing. So the goal here is that the data is secured at all times. Maybe this data could be some data which is stored in a GPU in the cloud. And to get the data to this GPU, we have to ensure that it's changing device. And for this purpose, we need remote attestation. And NVIDIA uses SPDM for this purpose. So SPDM is a protocol which supports remote attestation, device authentication, and key exchange. And it's to some extent similar to TLS, but it is especially tailored for use in embedded systems. So SPDM is not a simple protocol. Its informal specification is mainly written in English text, and it has more than 100 pages. In new versions, it's even more than 200 pages. So SPDM was created by a group which is called DMTR, and many players are in this group. So there's like Intel, Cisco, and Broadcom, and many more. SPDM was also not easy to implement because it had also some interesting design choices. There's, for example, the case that in the initial phase of the protocol, the size of all the subsequent messages is negotiated. So all the subsequent messages can only be passed with the knowledge of the size. In the project with NVIDIA, we formalized the subset of SPDM. And this subset was really a subset because we did not specify everything. So what is outside of the specification is the crypto part and the networking part, which is provided by the platform. The goal of this implementation was to have a really small SPDM responder, which can run on an embedded device without any runtime. And what we got at the end was the formal specification microflux, which was around 3,000 lines of code. Two-thirds were in the second specification, so the data flow part, and one-third the semantic specification. We have 60 states in the state machine, and the generated code were more than 130,000 lines of code. But only a small fraction of this was executable code. The most part, the smart contracts, is code which is just needed to do the formal application, but that's not the code which is actually executed at runtime. We did a lot of optimization to optimize the compiling so that they can really generate code which is really small. And at the end, we got an implementation of 25 kilobytes with bytecode. By using Spark, we can also ensure that there are zero runtime errors because we can automatically improve it. The case study and also the full specification that which we did, this can be also found on GitHub. So we see that we already are able to set up to simplify the process of implementing protocols in a correct and secure manner. But we still want to improve our concept. There are two things which we are mainly focusing on the next time. So one thing is doing high-level proofs. So for the state machines, we only focus at the moment on program verification to ensure that there are no runtime errors. But what we also want to do in the future is being able to define properties in the session specification and do things like model checking or cryptographic proofs to ensure that we actually specify the right thing. The second thing which we want to improve is the validation part. So far, the validation focuses on messages so that we can ensure that the message certificate is correct, but we want to improve the certificate generator and also the validator so that we can also check existing applications if they are actually doing the right thing, so if they implemented the right state machine. Coming back to my example of the beginning. So I think we don't have to live in a world where we have to feel that someone can send us an image and then compromise our device. There are solutions how to prevent these issues. I would love to hear your thoughts and questions. Thank you.
Okay, so any questions?
I went to SPDM. I was surprised because it really is, as you said, like it's a DLS variant. It used the same crypto, the same foundational sort of mechanisms, and that sort of made me wonder. And of course, you probably don't know because you haven't contributed to the standard itself, nor have I. Why the group didn't just big DLS and then added features on like exchanges afterwards, like for instance, because then their effort would have been like far less. They could have actually, or recognizing as an alternative, recognizing the similarity, they could have actually learned something from DLS. But I think they failed on both aspects, which is really sad. What was your thinking when you looked at this and given the prior work you did on DLS, I'm sure it's something, or you may have had similar thoughts.
Yeah, actually, I have the same point. So, looking at CDM, it looks similar at the beginning, but we made certain changes. So, we get the feeling that the goal of SPDM was really to make the methods some way shorter, so that's more. But I'm not sure if we really accomplished that. And also looking at the protocol flow, it's also that they made it more efficient really. So yesterday we heard about combining attestation and TLS to make it very faster. That's not the case for SPDM. It's separate handshakes after each other. So
it's like they managed to make it more complicated, more handshakes. It's like it's really surprising. A follow-up question, like with the way how you do the, as you explained, like I assume you put some additional constraints into the, let's say, C code to make that assertions. Is that roughly correct? Or is the record flux then different? How do I, if I have a program, like, let's say I've written a DLS stack, would I instrument that or augment that code with these constraints that you showed at the beginning of the talk, like the size constraints?
So the idea really is to have this form specification as the source for the code generation. The code generation we do is only in Spark. So you get Spark code at the end, and the Spark code can be obviously proven with the application codes which are accompanied by Spark. You can use the Spark code at the end to also combine it with existing C code. There's a C binding possibility. But what we actually do is really just generate Spark code which can be verified.
The Spark code would be directly combined to presumably to an intermediate language and then to the machine. Would that be then translated into, let's say, C and then something else?
But it's directly compiled into machine code.
Service vision. So I have a question about the verification goals. I think you started at memory safety, and then you talked about higher up the abstraction layers. I was curious if you had lower down stuff like sections, sorts.
So the code verifies is really, but it also status absence of runtime errors, so that we are really sure that the program doesn't crash by its once. We put on that also the function correctness to ensure certain properties, to ensure that the program is correct to some extent, as far as it is possible. But something like side channels is not important.
Just thank you very much. It was great to see the example because another was both there might be a mismatch between the two. And in fact, that's the way the options are built. Because a larger length, so we have a trailer of a by you to stash your options. And that's so my question would be, is your tool able to look at this cross-layer integrity things, or no, it just looks like a slice of them? Because that would, if that was in place and devices were built to just check this, typical options wouldn't be feasible in entering with the box. Just drop it.
Yeah. So each method specification on its own is just looking at a single message. But what we have is so-called type requirements. So you can define that the data part of a message should be actually represented by another message. So you can really define the connection between these two messages. And at the end, you should really achieve the thing that you want to feel that the language has the right value also in relation to the message that you actually transport.
Question. Okay. How do you position yourself against some of these other languages? Like if I think about Rust when it comes to memory safety, I think about F-star, which was mentioned earlier, to something that is more sophisticated. Like you are somehow in that sort of space.
So when compared to Rust is definitely not a lot better than what we have with C or C++. So it's already a level up. But Rust doesn't provide the same thing as Spark. For Spark can really improve all of the runtime errors. You can, for example, ensure that there are integers or code, which is not possible in Rust. You can improve it statically. You can check it at one time, but it's not just the same thing. In comparing it with F-star, I think that the Spark and also Reiher flux is more useful for engineers. So for F-star, I think we really the knowledge about how do I cruise, and that's not really needed for Spark, and that's needed for Reiher flux. So Reiher flux is really the idea that we can do specifications which are declarative and on high level, and you don't need to have the knowledge how to prove something.
You know, the practical side, you were mentioning support for TLS presentation language. Is this feature really established in the or is something you're working on?
Currently it's worked on, so it's probably finished in the next month or next week. So it should be there soon, but it's still in progress.
Could we use this a month's time to look at our tested TLS extensions and see, or would it be prohibitive to tackle TLS and not of TLS?
So it depends. So what we identify for the TLS presentation languages on one side it's not really complete. So we are currently also trying to solve the issues that when we use the TLS presentation as a source, we have to some extent to make it a very complex specification. So the difficulty is one so that some random preferences for other fields are not specified in the TLS presentation itself, but somewhere in the text in the set result. But at the end, the goal is really that we have a complex specification, which maybe needs some additional information provided manually. But then we can just do everything that we could do to the complex specification.
Since you're adding this, I'm working on the TLS 1.3 onboarding, or why are you adding this feature?
I suggest to continue the conversation during the lunch break, so we can move on. Sorry.